So this is the presentation on NDI and STI being given by John Shike and Sam Craig. And we're going to start with just kind of why IP and early adoption, and continue with a discussion about NDI and SMPTE ST-2110 in particular. And we'll stop for questions along the way and at the end. And we'll go as far deep into the weeds as the audience would like. So why bother? So going from our BNC cables to CAT cables, there's a variety of reasons for this. But if we go to the next slide, this is one indication. Positive Flux put this out back in 2015, and they were pointing out how quickly Ethernet was moving in terms of its bandwidth capability. So as compared to STI at, let's say, 1.5 or 3 gig or now 12 gig, we're looking at infrastructure now that's even on the order of 800 gig. So it was clear that the power and the capacity to not cover just one signal, but many, many signals over a single piece of wire became possible through the development of what's happened with Ethernet. Next slide. And then we took a look back. Sam and I were at Snell and Wilcox at the time. And in terms of the 2013 worldwide sales of SDI baseband equipment routers, as compared to the routers that were available, the switchers that were available in the IT world, even in terms of pricing, it was just a tiny piece of the pie overall. And we felt that that was an important indicator about where the industry was going. Next slide. So John Maya, CTO for networking and infrastructure at Imagine Communications, and this was a couple of years ago, he pointed out that ST-2110 is a better choice money-wise than a traditional SDI baseband router. As soon as you have about 500 or more connections, that's really a turning point where SMPTE 2110 really makes economic sense. And obviously for greenfield studio construction, consider that as we go more and more in the future, being able to find that talent that can work with IP equipment becomes more readily available. Next slide. And this, again, this is from a couple of years back, but comparing what you can accomplish with SDI and the price. Once you get to, this was for about 1,000, let's say, square type router, in terms of not only the cost, but also in terms of the size, in terms of the complexity, in terms of the space, in terms of the electrical requirements, there was a huge advantage to IP as opposed to baseband. Next slide. And this vision, and this slide is from about 2015, 2016. We were sort of in the tier 03 period, where VSF was really driving a lot of this. But the appreciation and understanding of where IP could sit was in all levels of production, of broadcast, of distribution, so that we no longer necessarily had to be SDI in the plant, but could be a true IP solution all the way around, from contribution all the way through distribution. Next slide. So early on, we saw AVB, we saw Sony's solution and MI, we saw Evertz with the Aspen, and they actually built some very impressive routing switchers using this technology, with a number of other companies joining into the community. And then NewTek with NDI coming out at about 2016, I believe, and SMPTE 22-6 at the same time, which is essentially SDI, embedded SDI, all but packetized into something that goes over a CAT cable IP. Next slide. Now, NDI has continued and continues to be very popular today. And really the fantastic thing about NDI is compare having an SDI, your BNC cable, and then having control, maybe it's a serial RS-422 cable, and then you have power, all of that in a single cat cable that all fits typically in typical 1G type switcher. So that difference, and the fact that you even have the power, you could have audio, you can have alpha channel, everything on a single cable meant that the NDI solution provided an ease of installation and ease of use compared to traditional broadcast technology. Next slide. So if you go to ndi.video/tools, you'll find a whole set of what they call the NDI core suite, tools that allow you to easily view NDI signals, create NDI signals, create test patterns, be able to contribute into a web conference or read from a web conference, analyze those signals. And let's just next slide, as one example. And I'll point out that a lot of these tools work best on Windows systems. However, the NDI tools are available for Mac as well. And what we call Studio Monitor is, in fact, a very powerful application, typically on Windows computers, that allows you to view an NDI source, allows you to record an NDI source. If you have a camera connected, like a PTZ camera, allows you to control the PTZ camera. You can position the camera. You can go into the configuration of the camera. So a lot of functionality, and not just the video, but the audio is supported as well. So a lot of functionality in this free tool on NDI tools. Next slide. NDI HX camera is a way to easily turn your iPhone into a camera. Again, it's a free product, and it allows you to have a source, an NDI source, that can be easily integrated into any kind of NDI system. Next slide. So interesting, this is a Teams meeting we're on now, and Teams supports NDI. So the various contributors to sources, or let's say participants in a Teams meeting or in a Zoom meeting, they can be strung out as separate NDI flows. So NDI for Teams, for Zoom, and for other web conferencing softwares becomes quite practical. Next slide. So the current version of NDI is 5, and one of the key features that version 5 provided was NDI Bridge. And NDI Bridge actually allows NDI signals to go over the internet. Traditionally, before this, NDI was always working within a specific LAN. But now with NDI Bridge, it's possible to actually send files. And actually, it's a bit like the way SRT works with receive and transmit. But essentially, that was a key feature of NDI 5. Now, NDI 6 comes out, should be out shortly, with high dynamic range and wide color gamut. Next slide. So for more information about NDI, streamgeeks.us was good enough to create 100+ pages about NDI. They call it the unofficial guide. So that's just one very easy way to get a lot more detail about NDI and its use and application. Next slide. In a comparison of NDI to 2110, I think what I would simply say is that NDI is easy and 2110 is powerful. So again, they're both broadband solutions as compared to SDI. Typically NDI, there's versions of NDI. Full NDI uses less compression. NDI HX uses more compression, so it's easier to get signals down into manageable size. For example, with NDI HX, typical 12G signal compresses down to about 350 megabit per second. So quite a difference. Obviously, it's compressed, and obviously, as a result of being compressed, there's latency. And latency is marked in different ways. HX has more latency than full. There's 2 versions of HX. There's HX2, there's HX3. It's mainly about the compression codec that is used. Obviously, NDI is essentially everything embedded to one. So you have video, you have audio, you have alpha channel, you have camera controls, you have your metadata. Essentially, all of that is over the signal cat cable and fits very easily into existing AV-IT infrastructure. So that single cable approach, where you even have power, means something like a church in an old structure putting in NDI cameras and NDI switcher. It's relatively easy to do. And it can work with a variety of references. Typically, many people use NDI systems with no reference at all. Instead, it simply finds NTP and all the inputs work basically like frame syncs. 2110, part of the complexity of 2110 is the requirement for PTP for timing. So it's a specific format of PTP, SMPTE protocol, but it's, again, 2110 was based upon standards from the industry, and use of PTP actually made a lot of sense. Typically, it's not used with much compression, so either uncompressed or very low compression with something like JPEG XS. And as a result, it's very low or essentially no latency per se, under a frame. Basically, though, all of the streams are independent. Their audio, video, metadata are separate streams, and this is really the big difference and one of the reasons that PTP is required. So, Sam, I think we're about a point where maybe flip over to you to continue the narration.
Absolutely. Thanks, Sean. I'm going to kill my camera again just so we can focus more on slides. But first and foremost, how well versed is this audience with 2110? Would you mind raising your hands?
I think we're pretty well.
All right. I figured this was going to be a really good group. So what we have here is a lot of introductory fundamentals. I'm going to breeze through these fairly quickly and get into more kind of use cases. How have these standards really been used in practice over the past handful of years? We know 2110 was ratified in 2017. We've been riding this wave and building out systems, but how does it all come together from a systematic standpoint, and what have we learned over this period of time? So just to breeze through really quick, we're all well versed in kind of the history so far. John went over history of video over IP, or really media over IP. But years ago, we had 2022-6. So very nice stream. We packetized everything together. It's data, audio, video, everything's there. Boom. Now I can pass that over a managed network. Very, very simple to do. So then we move, again, -6, it's a bundled approach. Audio, video, metadata from our bank and our sync and timing. PTP is not required. Use typical black burst and everything is fine and dandy. You'll see in the bottom left, published beginning in 2012. It's been around for some quite time, so all good there. But again, answering industry challenges and requirements. I think a lot of us have seen these slides quite a few times, but let's just dive in really, really fast. We want unchanged operator workflows. We still see that today. I'm used to pressing router heads. I want my signals to pass. I do not care about getting into deep weeds of control systems. I just want to see my signals pass. Great, we can do that today. Now, deterministic networking, no packet loss, low latency, minimal jitter. Great. We have non-blocking network designs. Awesome, it works, it's proven. Precision time for sync, great. SMPTE 2059-2, AES67, our classic PTP, it works wonderfully. System availability, great, -7 solves that. We even see that in cloud deployments now. And in security, great. Flow and host policies, we can dig deeper and deeper when it comes to how we're protecting our networks across managed systems. So moving forward, of course, I think everyone here knows AMWA, SMPTE, VSF, EBU, all these wonderful bodies have come together over the past couple of years to make this all sing nicely together. So fundamental time. Again, I'll breeze through this pretty quickly, but what is 2110? It's a suite of standards for IP transport and media workflows. We're simply breaking apart video, audio, and data into separate streams. Simple as that. But manufacturers can come together to create wonderful products that work together seamlessly and ensure the interoperability between them. That's been the fun part of this wave over the past couple of years, deploying large scale, small scale, medium scale systems, multi-vendor solutions. We have found what those little, not gaps, but what trips us up when making it all sing nicely together. We learn those lessons and apply it moving forward. That's the wonderful thing about this with open standards. We can always refer back to it. We have standards there for a purpose, and it builds wonderful systems. So our standards, this is not comprehensive. This could take hours to run through all of the different standards, but our classic -10, 20, and 30. These are our video and audio streams. -21 for our traffic shaping and delivery timing of video. -22, this is our compressed realm, getting into excess and how do we pass lightly compressed signals over LAN and WAN environments. -31, this is going to be our compressed AES-3 signals over 2110, and then -40, of course, our ANC data. So if we look at that down to the flow type, we've got our data top left, we've got our audio, we've got our video, and then there's our SDP file. I do want to tell you all a story about SDP files, but I'll get into that in a couple of slides. But long story short, we are just breaking apart these streams, and our SDP defines everything within that session. So quick comparison, of course, -6 is bundled, 2110 is essence-based, nice and simple. So again, -10, system architecture and synchronization, essences, RTP, SDPs, and PTP, so individual audio, video, and ANC tracks. Everything is carried as an individual stream. We've called these essences for a long, long time. I think that'll keep carrying over for years to come. But think of it this way, a 5.1 JPEG MP4 clip could have 9 essences. Video essence, 6 separate audio essences, 2 closed caption essences, English and Spanish. Long story short, -10 combines our RTP, SIP, and PTP. Need this in place to make it work. Then moving past that is our multicast. This has been a very fun topic to see over the past couple of years because multicast can be chopped up in many different ways. So if you look at this nice guide that Arista published a couple of years ago, when you start digging into actual deployed systems, you'll see down at the very bottom our 239.000 block. It's an administratively scoped, it's routable, and that is the recommendation. We've seen systems from 5-6 years ago that might use a 224, a 233, so on and so forth. You can kind of move around your different types of flows, but you run into potential roadblocks in the mix. So these days, we're typically chopping up all of our video, whether if it's HD, UHD, if it is -22, if it's -30, -31, -40, we'll design a block of 239 say 20, 30, 40. This is what we did in VSF plug events years ago, but long story short, this is what we adhere to. Nice and simple. Everything's published as a spec, RFC 5771, but our 239 block tends to be what we gravitate towards. Now, why is multicast so important? So get into broadcast. You have one-to-all within a subnet. Nice and simple. Then get into unicast. One-to-one and routable. Destination defined by the sender. We see a lot of, really, mostly unicast in cloud deployments these days, but you have overlay products that can bridge 2110 and multicast into the cloud. I won't dig too deep into that, but it is possible. Now, multicast is great. It's one-to-one, one or many, and routable. Destination is defined by the receiver. Long story short, multicast is a great fit for live, uncompressed media and managed networks. So there's a one-to-many fan out, sender does not know who needs to consume their outputs, and it's a connectionless protocol that's very lightweight. So context here is 4 different flavors, multicast works extremely well. Now we get into the fun part. How are we actually controlling these different essences or flows? Our classic here is IGMP. Many years ago, we were testing against version 2. This got into version 3, but the broadcast controller instructs destination to switch using ISO 5, and an IGMP join is issued to the network. Very simple to use. This leverages IGMP and PIM. You get IGMP join and leaves. It's simple and standards-based, works in layer 2, layer 3 networks, flexible and scalable. For many applications, this is the way to go. I've deployed many IGMP-based systems. It's wonderful, it's great, but it's not link capacity aware. It's not dynamically load balanced, and it is not source bandwidth aware. So if we take that with a grain of salt, yes, it's possible, but there are other methods of doing it. So then we get into software-defined networking. This has been a term that's been around for quite a couple of years, but we have a broadcast controller at top, we have a network controller, then the broadcast controller simply tells the destination to switch using our ISO5 join commands, and the network routes the new flow. Network fabric sets up the path. So this gives us very, very scalable ways to send our signals. Our network controllers also have system-wide IP views. So this is where your telemetry comes into place. I can sniff out what each flow is doing. It's topology aware and it's link capacity aware. A lot of fingers into that system. I only want those signals to go through that I tell it to do. Broadcast controller can leverage those northbound APIs. We've got broadcast views, broadcast logic built in. Now we get into tie lines, levels, matrices, audio follows, even audio mapping breakaways, all of that. So from our standpoint, from integrations, it's all down to what the customer needs. Do you need just a IGMP-based system? Great, we can make it work and it will sing beautifully. Do you want a bit more granular control on your network and have that mixture of the network controller and broadcast controller? Fantastic. There's a lot of products on the market that do software-defined networking. So it's always the choice of the end user, and we've learned our lessons over the years. All right, so SDP files. I'm assuming everyone has seen a variation of this slide before. We're all very well versed in SDPs and what they contain. Can I get another show of hands? Yeah, that's what I thought. So I highlighted a few of these pieces in here to really drive home a couple of lessons learned. So in -10, we're always defining session description protocol, an SDP file. This is our flow metadata. This includes a ton of information, sender descriptions, raster size, if it's video or audio or ANC data, frame rate, channel count, sampling, bit depth, colorimetry, IP address, ports, RTP payload IDs, and down to the grandmaster source and domain highlighted here in purple. So I'll use my mouse here and just kind of walk the line. I've got a description of what this sender pair is. This is a video stream. I typed in this as an example for 1080p at 5994. Now we get into our ports. So if you think about carving up that multicast address again, 239. Hey, there's a 20. Great, I can easily identify that that's a video flow. But I'm using port 50,020. Just again, I want to flag that flow down to the port value, and then what is the PID? 96. That's our industry adopted PID to use. But moving down here, I really want to drive home PTP. You'll see here we have a MAC address. That's our PTP grandmaster source and a domain. Now think about, let's say a switcher, for instance. Think about a switcher with 48 outputs, 96 outputs. Think about the people on the ground actually building those systems. And I have to go through each and every output from a commissioning standpoint. I've got to interrogate each one of these SDP files to make sure they're adhering to proper media node conformance. We'll get into the EVU pyramid here in a minute. I know everyone's seen that, but what happens is when a flow is switched, that SDP is sent by the broadcast controller. The recipient tunes its respective media inputs appropriately. It's all conveyed by the SDP file. But down to the purple domain of 125, that's kind of our default domain here. What can happen with PTP, the media node may send proper information about the grandmaster source, that MAC address you see right before it in red, but that could leave out the dynamic domain values, as in this case is 125, whereas from a system standpoint, this might have been defined as domain 127. So the SDP is stitched to the receiver, but there always runs that possibility of affecting downstream devices. Now, we all know in the case of PTP, usually the receiving device will lock to the external clock reference. Then it locks its internal device clock, which in turn syncs its media clock, and then subsequently starts stamping RTP it'll stamp our RTP clock to generate our RTP timestamps. So some devices might not act favorably in this case. Again, we have standards here for a reason. We want to conform to it. We want to be friendly media nodes. But little things like this can disrupt that systemization. We're gluing it all together. We've got to go through tons and tons of flows, tons of SDP files, and we might find that one outlier that is not actually updating what that domain value could be. So now we're posing a little bit of risk. So again, just lessons learned here. A couple of years back, I was in a foreign country. I won't name anything here, but same thing. We had a very friendly device, worked extremely well, and all of a sudden we start turning different receivers and transmitters on, and they were not reflecting in the SDP files what's actually active. So from a broadcast controller standpoint, we're trying to set a route, and oh no, that's not working because a different receiver is defined in the SDP. We had a difference in what the system understood about the whole thing. So long story short, I think everyone has lessons from the field such as this. Our SDP is so important. We want to update that in real time. This could use SAP to do that. We've got constant communication. It doesn't take a lot of bandwidth, but we all want to be friendly media nodes, and that's what it takes, especially on the integration side. We're finding what works, what the customer wants to do. So we take those lessons learned over the years and we build these wonderful systems. I've got a couple of examples here in a couple of slides, but at least wanted to share that story with everyone. That is real data pulled from the field, things we've seen. We've been able to overcome it, but it is what it is. So -10 is incredibly important. Now, to drive PTP home a little bit more, again, we could cover PTP over 3-4 hours. I think everyone's gone through tons and tons of presentations with this, but we're simply using PTP. We've got a master clock, we have a slave clock, we announce messages sent by the master, syncs are sent periodically by the master, delay requests sent by slaves, we get responses back from the master, and then hardware timestamping is essential. So long story short, we get reliable delivery, simple math, complex filtering, and we get accurate slave time. Years ago, we were looking at what's best practice from a networking standpoint. Do we want boundary clocks? Do we want transparent clocks? Most of the time these days, it's simply boundary clocks. Now, when it comes to distribution, again, spine and leaf topology, classic, works, it's scalable, but a couple of years back, we started introducing PTP feeders. Now, some of our early implementations had grandmasters wired directly to fabrics from a monolithic standpoint, wired directly into spines, but then we started bridging audio networks that still require PTP. So why not drop in a feeder there, define some PTP stack links for BMCA and failover purposes, and now it becomes a very scalable solution. So here on the right-hand side, we have a PTP distribution network simply showing Grandmaster 1 connects to Feeder 1, Feeder 1 connects to Feeder 2, which is then connected to Grandmaster 2. We have other nodes. This could be non-2110 devices that require PTP, but this gives us a tap to distribute that PTP outwards. Then we get into our red and blue networks. Feeder goes into the spines. Spines distribute that as boundary clocks into the leaves. And thus, in turn, we feed that in-band over to our media nodes at the very bottom. Now, from a real-world perspective, just to blow this out, same principle. Grandmaster 1 and 2 up at the top. You see our MAC addresses. We've even got IP addresses in here just to drive it home. We've got a physical connection to Feeder A. Feeder A connects to the core. Core distributes as boundary clock to all of our leaves, and then in turn, pipes it down to our media nodes. Now, you'll see here, we've got a switcher, right? It's taking out of band PTP. Great, but another reason why we always want to drop that feeder into the mix. It makes scalability much more achievable. Again, -20, I think everyone kind of knows this, but real-time RTP-based transport of uncompressed active video essences over an IP network. So SDP-based signaling method that defines image technical metadata, everything our receiver needs to know about the flow. This has been hammered home for years. This is raster size independent up to 32K pixels squared. Support for HDR that's prevalent out there in the market. We've been doing this for years, PQ, HLG, and it is format agnostic, 411 to 444, bit depth 8 to 16-bit, and whatever frame rate you want to throw at it. Now, the great thing about bit depth and tying back into John's conversation about NDI is we're very excited at ASG with the onset of NDI 6. That's been one topic of note for many years now. No 10-bit support, nothing above, no HDR. Well, now we're getting very, very close to having that released out to the market. So very, very exciting to bridge more and more capabilities within the NDI transport protocol. But long story short, back to 2110-20, bandwidth efficiencies. This is what it all came down to. Dash 6 years and years ago, 3.119 gigs per second versus 2110-20, we get about 2.6 with a little bit of overhead. So very, very nice way to pass uncompressed video over a managed network. Now, Dash 21, we don't see this a lot in practice these days, mainly from an integration side. But the early days of 2110, right before ratification and post, this was a very big thing. Do I have a narrow sender? Do I have an L sender? Do I have a wide sender? Some devices could send to others and vice versa. Long story short, this is just packet emission timing. Network traffic parameters, we want to ensure error-free data transmission through an IP network. I have a narrow sender to a wide receiver. Becomes very, very simple to do. Now, Dash 22, this came out a couple of years ago, but great. I want to pass JPEG access over 2110. So if I'm getting into more WAN type environments, I want to lightly compress my signals. Awesome. Compression's been around for a long, long time. It's not going away anytime soon. So great. Let's build this into there and have it all work. So RTP packetization and depacketization compliant with IETF standards and all the recommendations laid out by VSF TR08. So selectable compression ratios, good to go there. Now, Dash 30 is always an interesting topic. Audio has always been a fun one in broadcast media, but Dash 30, real-time RTP-based transport of PCM digital audio streams over IP networks by reference to AES-67. It's relatively flexible. We have 48K sampling up to 24-bit depth. Variable packet timing, that's our big one. Am I using 16 channel flows at 125 microseconds or 8 channel flows, 16 channel flows at 1 millisecond? So channel counts are based on packet timing. Again, very, very low bandwidth consumption. Now this is where it gets interesting. Early days of 2110, you saw different adopted levels, typically level A, level C. So 1 to 8 channels of 1 milliseconds, or 48K streams from 1 to 8 at 1 millisecond, or 1 to 64 at 125 microseconds. Great. But you had to have conversion devices in the middle. This is where a lot of your houses conform to a single house standard. Do I want a 16 channel house standard? Do I want an 8 channel? Do I want a 4x4 house standard? Luckily, NMOS stepped in and did some tests a couple of years back with ISO 8. This allows our broadcast controllers and our edge devices to do shuffling on the fly. Very simple to do. We've been used to this for many, many years. I want to choose a destination. How am I level mapping? What's my source? Bam, it all works. Or do I want to regroom in the control system and pick off stems and channels and create virtual sources? It's all doable now within the 2110 spec. Down to Dash 40, great. This is all of our ANC data. Real-time RTP transport, ANC data packets, creates IP essence flows carrying VANC data, just like we were used to in SDI. I want to pass closed captioning, time code, whatever I was stuffing in that VANC data space made it work, and Dash 40 simply supports that. Now, getting into Dash 7, we've probably seen a lot of these demonstrations at NAB, a lot of the VSF events, but seamless protection of IP datagrams. We used this back in the day when Dash 6 was very prevalent. It worked. I've got 2 networks. Awesome. But fundamental principle here is I have an edge device or host transmitter. I'm simply transmitting 2 copies of the source across 2 different networks. So 2 IP routers or 2 IP router cards, packets are received and joined at the host, packet by packet merging in arbitration, and works for individual packet or full stream loss. Long story short, about 1 frame through it. So Dash 7, great for 2110 applications. We even see this used in cloud and contribution environments just the same. Now I'm going to breeze a little bit over NMOS standards because I think we're all very well versed here in a lot of the improvements that have happened in the past couple of years. But basically, our fundamentals here, what we always stick to when speccing out new systems, is it ISO 4 and ISO 5 compliant? Has it been tested? Can we refer back to all of the showcases, the testing events? And most everyone participates extremely well in those events these days. But long story short, ISO 5, this is how our 2110 endpoints or our nodes are discovered and registered in an NMOS system, our control plane. ISO 4 is built on 3 APIs. We've got our registration, query, and node. And then ISO 5 is simply routing or controlling that device. So what I've always said over the years in these types of presentations is, I'm a connected media node. I come onto the network and I need to announce myself. Hi, I'm Sam. I'm from Texas. I like to wear cowboy hats and cowboy boots. I like to have a good time and tell jokes. Here I am. This is everything about me. All right, great. Well, I want to send you to do something. ISO 5 allows me to be controlled to do something like that. So simple hand wave and then do something after the fact. So what does that actually look like? Well, great. I have a sender at the bottom left and I have a receiver on the bottom right. I have an ISO 4 registry in the middle. Both of our nodes register all of their values. They're waving hello, telling everything about themselves. And then our application logic from our network controller, our broadcast controller, issues that ISO 5 connection command and says, node 2, you're a receiver. I want you to take these flows from these other nodes and senders. Simple as that. Very, very easy process. Now, I wanted to show where we've come in the past couple of years when it comes to the technology pyramid for media nodes. This has been around for a handful of years now, but the latest revision, version 3, released last year, we start at the top, media transport. Great, this is all based on a 2110 system. And then number 2, is it using PTP? Great, that's in the spec, it needs to be used. And then number 3, operational control. Are we adhering to AMWA networked media open specifications? Does it leverage NMOS? Most of the time, yes. And then configuration and monitoring. We want agile facilities. And then lastly, security. Now, we take a further granular look at that. What does that actually mean? Media transport is single link video over -20, software friendly -21 wide video receivers, universal multi-channel and low latency audio under -30 level B, and then stream protection with -7. Time and sync, very, very straightforward. PTP monitoring, we've got PTP v2 configurable with SMPTE and AES profiles, multi-interface PTP redundancy, and then synchronization. All those fun bits. Then we start getting into more of the technical weeds when it comes to control. Most devices adhere to 2110. If it adheres to 2110, it's got to support PTP. Well, how do we control that? Our discovery and registration for ISO 4, do we have, BCP group hint tags in there? Do we have connection management to tell receivers what to do? Do we have device control? Do we have audio channel mapping? Do we have topology discovery and LLDP? Most of the time, yes, we're about halfway there. But then you get into level 4, and that's where it's not as widely adopted. Configuration and monitoring can be IP assignments, low-level configuration. DHCP is great, plug and play, or ISO 9, which has been deprecated. We get into open configuration management and then open monitoring protocols. These are the big ones. And then lastly, security. All of our security tests, our safeguards, and our secure API calls conforming to BCP 003. Where are we now? So we do a quick comparison. That was 2020, coming into 2023. It's changed just a little bit. Now, media transport is fairly the same. We get single link video at -20 and then friendly wide receivers for -21. That's all good to go. None of that changes. Time and sync, much the same. Operational control, that's a little bit different. ISO 4 for discovery and registration, ISO 5 to tell a receiver what to do. But now we get into device control, open methods. We're starting to get into a world where it's not just 2110 or media over IP. IS-12 gets into much larger agile environments. I know this is still being worked on. I can't really dive into the weeds too deeply, but even with cloud-based deployments, this is one topic we are starting to look at. Could IS-12 bridge that control gap across many different multi-vendor solutions, all living in public cloud or even private cloud? But as I mentioned before, also audio channel mapping, ISO8, that's great. I think there was an IP showcase a handful of years ago that actually showed it at one of the trade shows. Awesome. But now, level 4 into configuration and monitoring. The holy grail here is plug and play and let the system sort itself out. We're still deploying statically assigned media nodes in 2110 systems. We have seen near zero touch configuration and deployment of systems, but there's still a lot of chefs in that kitchen to make it work. The end goal is to really have this be a self-aware system. I plug something in, it's registered, it's great. But configuration monitoring is a big one. It's coming along, but how are we doing open configuration management? A lot of controllers out there will control through ISO 5, and I can configure multicast, our ports, our names. It's wonderful. It does work, but there's got to be a better way to do it. Then you get into open monitoring protocols. Is it open telemetry, open config, syslog, I mean, back into SNMP, huge ones. And then security. We're starting to get a little bit of that red in that bottom rung of the pyramid broken down, but this is where we get into our cybersecurity protocols and our authentications, our authorizations for streams, vulnerabilities, and encrypted control communications. So long story short, between even 3 years when these 2 different pyramids for media nodes have been published, we're starting to see it come down just a little bit, and it's more widely adopted. So bringing this all back together, how does it actually look on paper? How are we designing systems for end users to use? And here's just a great real world example. No customer names on here. This is just an example from stuff we put together internally at ASG. But what if I had a customer furnished broadcast LAN, a control network? That's our kind of outline across all of the devices. But in the middle, I've got a control system. I've got HA instances, and then I've got PTP grandmasters up at the top connected with antennas. We have some PTP feeders, and that serves as our distribution layer for timing. Then that's wired into our media networks, and then we distribute that across all of our different leafs within the spine and leaf network. So we're able to isolate, well, what's a lower bandwidth media node? How is it getting its PTP? Is it in band? Is it out of band? Great, but let's get a smaller switch that supports 1 or 10 gig. Lump all of those devices there, -7 supported, and then we start getting into 10/25 gig endpoints, higher step up switch, and then more beefy switches to support our 100, 200, 400, 800 gig devices. So long story short, in practice, what we've learned over the handful of years is the standards are there for a reason. The recommended practices are there for a reason. So now we're able to take those lessons learned, go talk to end users. What do you want to do? Let's make that dream a reality because we know this is proven. I mean, this was stamped in 2017, been writing it ever since. So now it's up to us to just keep telling the story, keep deploying wonderful systems and having wonderful, happy end users. So last bit here, just a couple of pertinent links for additional reading. If you're curious, I know we'll publish some of these slides here. And that's kind of it for the slide deck so far. So thank you for listening for a couple of minutes and let us tell a couple of stories. But do y'all have any questions?
We'll throw the floor open to any questions that you may have based on the conversation.
Well, I have one just starting off.
Can you come over to the computer?
The microphone over there. You mentioned at the beginning the cost entry point at a facility at about 512. What do you see towards bringing that down to smaller facilities? I know that Netgear introduced the switch at NAB that will do 2110. Are we seeing more affordable switches on your radar?
We absolutely are. A lot of those comparisons came out a handful of years ago. Think about a dual frame Envision router, an Evertz router, a Grass router, a Snell router. Those had a very, very high price point to it. So we started gauging if we were to mix SFPs, QSFPs with a COT switch plus IO, keeping a baseband facility, but we simply swap out the router. What is that comparison? And 5-6 years ago, it was about 1056 or 1152 squared. Was kind of that parity mark. And then a handful of years back, it got divided by 2. That's where that 512 squared came out. But even 3-4 years ago, you started hitting the much lower prices for similar systems. Think a 256 squared router, even lower. I can now have a 16 port QSFP switch at a half rack width that's nearly on par with what a baseband router would be at the time. So to answer your question, yes, it keeps coming down significantly year over year. We get higher bandwidth, we get better pricing on the equipment, and thus lower price for the customer.
And a follow-up question, staffing for these facilities, particularly a smaller facility, staffing a facility, say a corporate studio, staffing a facility with someone who can understand this architecture and make reasonable troubleshooting solutions if something is wrong,
Of course. So just to be very, very transparent, that is still a topic of note that we get asked all the time. It is a very specialized subset of skills. We've been really going these rounds for a good 8 years. It's a transition to more IT-based workflows. So can you teach a broadcast engineer IT networking and vice versa? And there's been a very significant challenge. But the good thing is most of the tools out there on the market make it a little bit easier to understand. So if you have at least some sort of knowledge base when it comes to IT and video, you've got tools to rely on and plenty of resources, even on the open internet, to really sharpen those chops. So yes, it's still a topic, but it's becoming a little bit easier over the years to kind of dip your toe in the water and really be involved in those workflows.
And I think that's an example where, something like NDI has that simplicity versus something like SMPTE 2110 that has that versatility. So with regard to NDI, you don't even need a reference because the system essentially, the various production switchers that built around NDI have frame syncs. And they all run without any specific reference, and they'll time everything out to make up for that. SMPTE 2110, we saw that the PTP architecture in itself can be a little bit complex. But of course, the advantage there is that you have all of those individual essences or flows or signals available individually, separately, and you don't need to de-embed anything in order to get to a particular flow and package it in any way that you wish. So, and looking into the future, you have more and more IP savvy engineers that become available. So in that sense, that complexity, while the complexity comes down, the talent to support the technology, I think, increases.
I feel compelled as a Netgear guy here to a little bit of an advertisement, I guess. I don't know. The 2 SMPTE switches are coming out end of this month. First of all, it's 2 models, support 2110. But I think the groundbreaking thing we're doing is allowing you to set up the switch much easier. So with the profiles we've had for years for NDI and everything else, it's basically a couple of clicks and we'll set the switch up for you for 2110 as well. So you don't have to have all that years of knowledge as an IP guy. You'll need to know some of that, of course, to maintain it. But I think that's what's will help a lot of smaller broadcasters get into 2110 faster.
So kind of democratizing the support, right?
Yeah, well, and we also have a team of people that are overwhelmed all the time, that are answering questions all the time for setting up switches for AV. They know IT because they've been in Netgear forever, but now they know AV as well. So they've installed equipment that you're probably installing as well and know that, what firmware are you using or what setting are you using? So that's going to carry through eventually with 2110 as they become more familiar with it.
And that's the way to do it, honestly. If you're not sitting in the CLI interface and going line by line for configurations, you make it easy for the end user to understand and operate. That is so key. I mean, I think a lot of us have spent way too much time drawing things out, sitting in front of a CLI for hours on end and troubleshooting. Well, can't you just have a golden image and ready to go? Think about what Dante did years ago. Make it very simple from a networking perspective. Great. You need audio over a managed IP environment? Great. Here's the switch to use. Here's the simple way to configure it, and you're off to the races. So,
Well, speaking of Dante, Dante AV is now a thing. Have you integrated that anywhere?
Not the AV portion. We are one of two selected integrators for the Dante Connect platform that was released at NAB in 2023. So cloud-based environments. You can deploy on-prem. We've done that before, but you need to distribute a very large Dante environment across the open internet and leverage the public cloud. Yeah, we've been doing that for many months on end since the product was released, and it's incredible to see. If you have an on-prem Dante network, a full layer 3 managed environment, and now I need to tap that out and send it somewhere else to another facility, and I want to bounce it off the cloud with less than 40 milliseconds of latency, great. It's absolutely supported, and we can help along the way. So yeah, it's a really cool world these days to see how cloud is leveraging a lot of these large scale environments. And even down
application, I was going to say, Sam,
Yeah,
application wise, we've seen the Dante AV Dante video more in the AV area alongside of HD-based T and SDVoE, IPMX, and other formats that are being supported by companies like Crestron, et cetera. With NDI, we have seen NDI actually in broadcast. So NDI and SMPTE-2110 are the two, let's say, IP over video formats that I'm seeing the most often in sort of the more broadcast arena.
You hit it on the head, John. When it comes to cloud-based deployments, and that's what the team I interact with day to day here at ASG, it's all about the cloud. But it's really software-driven solutions. Does it live in the public cloud? Is it private cloud? Is it bare metal hardware? Are you doing a hybrid deployment? Well, how do we stitch that all together? You have so many flavors of media over IP. There's a very large system we did last year. It was Zixi from a transport perspective, but that all got converted to NDI because it was lightweight and low bandwidth to pass between different instances in public cloud. And it was easy to work with. Single discovery server, it shows every device, every flow within the system, and I can route just like I would a baseband or a 2110 router. It became very simple to use. But even down to intercom, you think about a cloud-based intercom. I need ground to cloud contribution or even just a pure cloud solution, but how am I getting my mix minus? How am I getting my interrupts to come through it? Well, you've got great protocols to do that. You've got Opus, you've got Dante for IO, but couldn't I just leverage NDI? And sure enough, we did just that. One intercom provider recently started supporting NDI. So we had outputs from our production environment, think audio mixers, vision mixers. We could mux that within the cloud platform, packetize it to like a 16 channel flow, and then pass one stream to the intercom system and pull off mono channels out of the stream, and then send our NDI streams back into the production environment. So it became more of a glue to get everything to communicate nicely with one another. And the video never suffered degradation. It was great quality, and then broadcast quality distributed day in, day out. This customer was doing, I think, 250 broadcasts throughout an entire year, and they embraced it. It's wonderful to see.
Right.
Yeah, I have two questions. The first one's about traffic shaping, which you mentioned in one of your slides. One of the techniques you mentioned is the narrow linear technique, which distributes the packets over the entire frame, including vertical blank. Question is, have you seen that used in practice anywhere?
Honestly, I have not.
Okay, good.
It's,
So,
it's,
yeah, that's
Yeah.
a manufacturer that's developing a new product, you wouldn't say they would need to have that feature in their product. Is that a fair assumption?
that's a fair assumption. I started deploying IP-based systems in, let's see, about 10 years ago. A lot of MPEG-2 and MPEG-4, just transport stream systems across, private wide area networks. But then we got into the 2110, well, really the -6 domain. That seemed to work. But then in 2110, it was only for a handful of years in interop events that it became a really big issue. And so once vendors started realizing, well, this is the recommended way of doing it, I want a narrow transmitter and a wide receiver, and that ensures it's always going to work. That's typically what we've seen in the field over the past 3-4 years. It's not really a big deal anymore. I think the last time I saw it was at a Super Bowl, gosh, 4 years ago. It was in pre-pandemic times. We found a solution for it in the field, but yeah, we had 2 vendor products that could not communicate in terms of their streams. And so we had to put a processing block in front of it, and that groomed everything, and it worked magically. And we added 1 frame of delay, which was not ideal. But yeah, the NL technique, I have not seen it in the real world, to be honest.
Okay, good. Let's hope it goes away. Second question, which is related to the buffering you mentioned. One of the common practices in 2110 is to buffer at every processing point. So if you had a format converter followed by a keyer, you would frame sync in both cases. That's not the way we were talking about it when we were having the initial meetings in 2110. The question is, have you seen any pull from the customer side to try to avoid those redundant frame syncs?
A couple of times over the past couple of years, but most of the time these days, it hasn't been much of an issue. As long as we're ensuring that there are clean signals entering the fabric, buffering does not tend to be such a big deal as it was 5-6 years ago. So not a lot of ask anymore. It's still there, but not much of a need these days.
Is that because we're seeing more consolidation on the products that can do multiple functions in one go, as opposed to chaining together 3 or 4 2110 functions?
That's exactly it. You have one device that's a Swiss Army knife that does many, many different things. So I don't need to pass, a signal into a traditional frame sync and what we used to call a proc amp and so on and so forth. Everything's kind of built in to just do all of that. Signal in, process, and then out. Everything is aligned, good to go.
Okay, thank you.
What is ASG's process for testing, evaluating, and ultimately approving IP equipment that'll go into customer installations?
Oh, that's a great question. It depends on the use case, to be very, very honest. When we're interfacing with end users that come to us for assistance in validating products, we'll typically develop sandbox or proof of concept environments, but we do a lot of internal testing just the same. That's one of the great benefits of being such a widely received partner. We have our ears to the ground and we hear what's coming down the pipeline. And a lot of vendors will come to us and ask, would you mind running this through the paces and let us know of your candid feedback? And I know our cloud team, what I oversee day to day, we do testing just for fun. We've gathered a lot of insights over the years from different deployments. Everyone's got a different background. And so if we catch wind of, hey, there's a new product coming out, or an ISV comes to us, great, let us get our hands dirty. Let us do an internal proof of concept. We'll dream up some type of workflow and then put it through its paces. So not deep QA testing that you would see on the vendor side, but what have we seen from our end users? What are they requesting? Does it live up to what they're asking for? So we've got some boilerplate templates that we can run through, and if it checks the mark, great. We'll let the vendor ISV know, and then go from there.
Well,
So
Sam,
it's-
how about if in the process of an integration, if we have questions or issues,
sure.
how
for
has
sure.
has the response been from vendors to helping us to solve those?
Oh, it's been amazing. If you look at our recent PAC-12 deployments, we did an entire sandbox and tested various vendors' equipment against what the customer was trying to do. So is it just a gateway? Was it just a multi-viewer? Was it a processor? Is it a vision mixer? So on and so forth. We find what's the best in breed solution. Let's get our hands on some actual equipment or some software and run it through its paces. Does it meet what you're doing? Does it check all the boxes? Do we see an issue? We'll contact the vendor and see what we can do to resolve it. But yeah, long story short, we love testing, especially from the eyes of an end user. That's just gold to us.
Right, is that your question?
Yeah, I have a question on your Dash 7 protection. You've got your different classes, you know, A, B, C, D. And I'm sure it boils down to how, you know, what you're doing, but what kind of requirements are your customers throwing at you for how much buffering they want on their Dash 7? Does that make sense?
Yeah, to be honest, I have not ever been asked that from a customer. Even when I worked on the vendor side, it was more of, does Dash 7 work? Can I yank this fiber over here and will video continue to go? And if it passes that basic test, then I guess Dash 7 works. So
Okay.
yeah.
A more controlled environment, you know, in a studio, you know, you can get by with less buffering, but they have like their class A is like 10 milliseconds difference between streams you have to make up for. All the way to class C is like 150 milliseconds.
Yep.
It's like that, but you don't really have much visibility there.
Not honestly, not from the field. That
Okay.
hasn't been asked, at least specifically to me, John. I don't know if that's been asked of you, but yeah.
I can answer it that one if you like.
Sure.
So this is Jed with Nextera. So when we came up with those specs for 2022-7 back 8-9 years ago, the switches were quite slow to route an IP signal through an IT switch. It could take 20 microseconds, 30 microseconds, somewhere weird as much as 50. So we said, well, you know, how many switches do we think we're going to have to go through? Class D is 150 microseconds. That might be okay, but in a big spine leak, maybe it's not. So we came up with some other classes. But very quickly, as soon as people saw how bad it was, Arista, Cisco, Juniper, all the others, they drastically removed their latency, their switches, mostly because they use Broadcom chips. They got it down to around the 3-4 microsecond. So it's pretty hard to get to 150 microsecond if each switch hop is 3. So I've never seen anybody use more than Class D, which is 150 microsecond.
I think that's a great point about the fact that there's been really good reception from the switch manufacturers, you know, from early days like Cisco and then Arista. And then, of course, John was talking about Netgear. So that, you know, to support media through the switches. So I think that's great that that improvement happened so quickly.
Good questions?
I got one more. I'm curious what you guys are seeing is the tipping point for broadcasters to switch over to IP. And certainly I'm focused on Netgear, but for smaller broadcasters or medium-sized broadcasters, not a huge NBC or somebody else, but the smaller ones or medium ones, greenfield I get, but for existing broadcasters to switch to 2110, what are you guys seeing is that tipping point?
A lot of times it's protecting investments. We know SDI is not going away. You can read about that all day long. It's going to be here for a while, but you want to protect the budget you're given and ensure that you've got lifespan for that product in your workflow. That's where a lot of times we see the peaked interest. We know this has been proven. A lot of people did not want to be the guinea pigs, you know, back in 2017, 2018, but we're years ahead of that now. Proven, it's nearly simple to do, and it's widely supported. So great, use off-the-shelf technology and then vendor-specific products that conform to standards. It just simply works. So a lot of times that's one key piece. Honestly, that's kind of the biggest one I've seen in the past couple of years is just future-proofing investments to make sure systems are going to last for the next 5-10 years.
That makes sense. Thank you.
Any other questions?
On the topic of SDI, I'm wondering if you guys have done many mixed SDI 2110 or mixed SDI NDI installations, and what sort of issues or rules of thumb you've come away with those.
Actually, yes. Here's a quick story for you. This is probably 3 years ago. We had an end user that had a very expansive baseband infrastructure, and they wanted to purchase some best of breed multi-viewers. But those multi-viewers were only 21, or really media over IP. So you could throw RTSP, RTMP, SRT, 2110, whatever you wanted to throw at it. But they needed a gateway solution to do that. So they had a baseband router, very large infrastructure. They dropped in some gateways in the middle. You had IP-COTS network, and then you had multi-viewers and other processing products with this 2110 island. So control was the big piece there. How am I going to take a studio camera that's wired with a baseband interface to my router and send it all the way to a multi-viewer and back to a monitor with nearly one press of a button? And sure enough, we found a broadcast controller that would handle tie line management just like we've been used to for many, many years. Didn't matter if it was 2110, didn't matter if it was baseband, it's just a tie line between two routers. And lo and behold, it worked. So control was key for that customer. Yes, it's all standards in the middle, it all works, it'll sing nicely, but how is that operator in the hot seat actually going to take that camera to the multi-viewer up to the monitor in 1 or 2 button presses and remove a lot of that complexity? So we've seen a lot of environments such as that. I'll be very honest, John Shike can probably speak a little bit more when it comes to on-prem NDI, but even in the cloud, like I mentioned, we're gluing a lot of systems together with NDI within public cloud. And then again, control is still key. So you've got this monitoring and control layer that sits over the top that's going to talk to on-prem devices, on-prem router controllers, all of your interfaces for ingest in the cloud, your processing elements, and all the way back to the ground. That's where control, again, becomes very, very key. Could have 2110 on-prem, could have baseband on-prem, could have NDI in the cloud, could have transport mechanisms in the middle for contribution and distribution. It's all key to that overlay and how the operator can visualize and control that network. So John, I don't know if you've seen anything else.
Well, we've seen more and more conversion equipment. So, there's going to be issues of latency as we go back and forth between different formats, but the conversion equipment, not just SDI to 2110, but NDI as well. And so NewTek and now VisRT and other companies are providing those kind of solutions. And even within the computer, if you will, doing these kind of conversions, et cetera, becomes more and more possible. So it's, there are concerns, right? And mainly toward, the issues introduced with compression, with latency and so on. But other than that, it's not a problem. And let's just say in a facility where you might build on-prem on SDI, on 2110, obviously there's probably still some analog or I would say SDI type equipment, baseband equipment that's going to be integrated there. Really not a problem to have NDI as part of the system. So I would say that more and more one realizes that both are living in the same facility fairly easily. I don't know. I hope that's helpful.